What is meaning of diffusion? Diffusion is a direct proof for intermolecular motions. As we know, the matter molecules are always moving, even in solid state. We have told you in earlier lecture. What is diffusion? Mixing of two substances due to motion of particles of substances is called diffusion. So, diffusion is a direct proof of intermolecular motions. Diffusion is a direct proof that molecules or particles of substances move. They are in motion. You see, one example. Suppose we have some fresh water, pure water in a beaker up to level A. Whenever we talk about water, water is always pure. But water available in our surroundings is not pure. Water from your wells, from your tap water, from lakes, from sea, from rivers, you do not get pure water. Whenever we talk about water, we take pure water. We consider pure water. Suppose we have pure water in a beaker A and we add some amount of sugar already kept in a crucible. Suppose we add 100 gram of sugar in water vessel. Suppose this is 1 liter in volume. Volume of pure water taken is 1 liter and we add 100 gram of sugar in this. As soon as we add sugar in this vessel, the water level rises. Water level rises up to mark B. Initially, water level was up to A. But as soon as we pour down this 100 gram of dry sugar in it, suddenly its level rises. After hours, if you again observe this thing after hours, not after minutes, after hours, if you again observe it, you will find there is no heap of sugar. Whole amount of sugar heap gets disappeared. Now the question arises, where all of the sugar particles have gone, and when the heap of sugar gets disappeared, the level of solution is same as was initially of water. There is no any change in the level of solution and water. Volume of water is unaltered after dissolving entire sugar. Now the question is, where sugar particles have gone? If sugar particles have gone somewhere, they will need some space. They will need some space because matter occupies space and has mass. Sugar had 100 gram of mass and its volume was something. Sugar occupies space, but the volume of entire water is unaltered after dissolving sugar particles. Now the question is, where all the particles have gone? Now we are bound to say that there is some space between water and water molecules. Water and water particles were moving, and entire sugar particles have got disappeared, and they have occupied the space between water particles. Sugar particles have gone in the empty space between water particles. Sugar particles have gone into the spaces of water. So we prove by this experiment two things. What are two things we prove by this experiment? First, particles are moving. Entire sugar particles have moved. They have left their original position. They have got disappeared because they are in motion. And another thing, there is some already space between water molecules. That is why the entire volume of water remains same, even after some occupied place by sugar particles. Some sugar particles have got occupied a new place, but volume of the water is unaltered. It means there is some empty space between molecule to molecule. Between water molecules there is some space, and all disappeared sugar particles have got place in those spaces. Two things we prove. We prove two things by this experiment. Now, another proof of material particles are in motion. This is property of particles. This is property of particles that they are in motion. First example, this one. Why first this? Why not solid first? Because this example is easily practicable and can be seen by our naked eyes. So, this is our first experiment. KMnO4 is a solid crystal of reddish brown color. If we keep some granules of potassium permanganate into clear water, potassium magnet crystals dipped into a beaker containing pure water. Pure water is colorless. Water has no color. If we add some particles, some granules of potassium permanganate in colorless water of beaker, gradually, gently, potassium permanganate molecules are diffused. What is meaning of diffused?
Mixing.
Potassium permanganate molecules move and go into the spaces of water molecules. And finally you can observe entire solution becomes of purple color. Are you accustomed about purple color? It is reddish, not red. It is reddish. Entire solution becomes reddish. We cannot say it reddish, we say it purple. Pink color, not purple, pink color. Pink color, not purple, pink color. Entire solution becomes of pink color. And another example. Why another example? Why not only one? If you do not get potassium permanganate crystals, or potassium permanganate crystals are not available easily for you. If potassium permanganate is not easily available for you, then you can experiment. Secondly, you can take copper sulphate. Copper sulphate is easily available in your lab. Both are easily available in your lab. But copper sulphate can be purchased from a market. It is of greenish color. Copper sulphate crystals are some greenish color. Copper sulphate crystals are of some greenish color. White and green crystals you can see. If take a teaspoonful of copper sulphate powder and add it into a glass of pure water. After some time, you can observe the entire solution is of blue color. Entire solution becomes of blue color. Entire water becomes of blue color. How it had been? Because of diffusion. Because of diffusion of copper sulphate molecules into spaces of water molecules. What is meaning of diffusion? Motion of particles. What is cause of diffusion? Cause of diffusion is motion of particles. These two examples are quite easy to experiment simply in your lab. In your home also you can. Now you can see third example. For this experiment you need such type of pots which are connected. Pots A and B are connected by a tube, and tube can be closed by tap T or tube can be opened by tap T. Now close the tap T of tube and pour down a milk of white color, milk in A and pure water in B. This is of white color and the water is colorless. The level of both liquids in both the pots is same. So after opening of T, none of the liquid will flow towards another. Since level of the two liquids is same, so the flow of milk towards water or flow of water towards milk is not possible, because pressure at the both ends of the tube are same. So direct flow of water towards milk or direct flow of milk towards water is not possible. Now open the tap and watch. Just keep yourself mum for some time, for 45 minutes or 1 hour. You can watch. You can see gradually the color of water is changing and it becomes milky. How was it possible? Because certainly some milk particles have got diffused in B, but level of the two pots is not altering. Level is maintained. It means some water has also been transferred by diffusion into A. This is very amazing experiment, and you can connect two pots by a plastic tube, and you can do this experiment in your home also, and you can verify my statements at home. Diffusion, again, diffusion is the direct proof of motion of the particles. Some particles of this go in this direction and some particles go in this direction. This diffusion is similar. This diffusion is similar to that process. Which process? Men coming from one lane towards market and men coming from opposite side on the same lane in the market get diffused in market. They have got mixed up. In the similar way, material particles are mixed with each other. What is the reason of diffusion? What is the reason of diffusion? Motion of particles. There is only one reason of diffusion: motion of particles. If two teams of ships or goats, if you have two teams of ships and goats separately, and all they are sitting in their own position, they cannot diffuse into each other. But if we free them and to move on a same route, the both team will get diffused because of their motion. Similarly, diffusion of two liquids or diffusion of two gases or diffusion of two solids is due to motion of the particles of substance. Another example for gases. Diffusion of liquids is quicker in comparison to diffusion of two solids. Diffusion of solid particles takes a long time. This cannot be observed very easily in very few time. In hours, in months, in years, you cannot observe. It takes long time, but it takes short time. So diffusion of two liquids is quicker in comparison to diffusion of solids. And diffusion of two gases is very quick. Diffusion of gases is very quick. Why? Because the motion of gaseous particles is quite high. Motion of gaseous particles is very high in comparison to liquid particles. Now, take some examples here. Diffusion in gases. Diffusion of clouds are one of clear examples. Just see in the cloudy atmosphere and watch two pieces of big clouds moving towards each other. After some time, there is no separation between the two clouds. They get diffused into each other and they seem like one piece. That is an example of gaseous diffusion. Another example, a smell of scented sticks, जिसको हम लोग अगरबत्ती कहते हैं. A smell of scented sticks prevails in our surroundings. That is also an example of diffusion of gas into gas. Now third, ammonia has unpleasant smell. If you smell ammonia, you will feel its unpleasant smell. And also there is another gas named as hydrogen sulphide. The smell of hydrogen sulphide is similar to the smell of rotten egg. If you do not have any experience of smelling of rotten egg, what will you do? You can smell a piece of kala namak. Kala namak is also known as rock salt, and some amount of rock salt would be in your kitchen. You can smell a piece of rock salt. The smell of rock salt is similar to the smell of rotten egg. And a gas, hydrogen sulphide, has the same smell. Now, at 1 atmospheric pressure, both gases are taken into separate pots at 1 atmospheric pressure. Initially, if you smell here, you will find the smell of ammonia only. And initially, if you smell here at the end of pipe B, you will feel the smell of hydrogen sulphide only. But if you open the tap T and let both of the gases diffuse, permit both the gases to diffuse by opening this tap. Only after few minutes, just you go and smell here, you will find the smell of both the gases. And also here, you will find the smell of both the gases. This is also a good example of diffusion of gases into each other. What is the reason of diffusion? What is the reason of diffusion? What is the reason of diffusion? What is the reason of diffusion?
Motion and particles.
What is the reason of diffusion?
Motion on particles.
Motion of particles. Yeah. Motion of particles. What is the reason of diffusion?
Motion of particles.
Motion of particles. Diffusion in gases is quick in comparison to diffusion of liquids. But diffusion of solid to solid is quite slow. If you take a gold foil and 2 lead plates, just insert a gold foil between 2 lead plates and press it and leave it for some years, 2 or 3 or 4 years. After 3 or 4 years, if you try to separate them and you separate it, you can observe gold particles on the surface of lead particles, on the surface of lead plates, and lead particles can be observed on the surface of gold plate. This is the example of diffusion of solid particles. Why did diffusion takes place? Why diffusion takes place? Why diffusion takes place?
Because of motion of particles.
Because of motion of the particles. Why diffusion takes place?
Motion of the particles.
Because of motion of the particles. Diffusion is a proof of motion of the particles. Now, furthermore, three states of same substance. Solid, liquid, and gas. Ice is solid state of same matter. What is name of that matter? Matter is H2O. Formula of water is H2O. Name of matter H2O. Ice is solid state. Water is liquid state of the same matter. Matter is not changing. Its state is changing. Vapor or steam matter is same as H2O. Matter is not changing. How can you prove that matter is not changing? Because taste of steam, taste of water and taste of ice will be same. If you use litmus paper, it will not change the color of litmus. Also, this water will not change the color of litmus. Also, vapor will not change color of litmus. It means the matter is same. Milk is another matter, but curd is another matter. There is change in matter. But here, matter is not changing. Its states are changing only due to difference of temperature. Ice is that state of H2O which is at less than 0 degree Celsius temperature, but at 1 atmospheric pressure. The temperature of ice is less or equal to 0 degree Celsius at 1 atmospheric pressure. But liquid state of H2O ranges from temperature greater or equal to 0 degree Celsius, at 1 atmospheric pressure. At 1 atmospheric pressure, water state remains ranging from 0 degree Celsius to 100 degree Celsius. If by heating water, if we supply some more thermal energy to water, it gets converted into steam, and in steam form H2O molecules are wandering with very high speed in zigzag motion. In steam state, the motion of molecules is zigzag. That is also called rapid random motion. Water particles are executing random motions, but their speed is quite high in comparison to water state. And in the solid state, the motion of H2O particles were quite low. In solid state, the speed V, translatory motion 0 हो जाता है. Molecules vibrate only at their own position in solid state. In solid state, consider a glass piece, or consider a copper piece, or consider an iron piece. It is made up of iron. Each particle is named as Fe, iron. Each atom is named Fe. There is some finite space in solid state also, but these particles or atoms cannot execute translatory motion. What is translatory motion? They cannot leave their own position, but they vibrate in their mean position. They vibrate like pendulum. But you cannot observe their oscillations by naked eyes, because you cannot observe atoms. We can prove by some experiments, but there is motion. In solid state, particles execute vibratory motion in their own mean position. They cannot leave their places. But there is motion. That motion is vibratory motion. That motion is not translatory motion. Just like pendulum has vibratory motion. It is not going from one city to another city. it is not going from one place to another place. Point P, the peg from where it is hanging, peg is at the same place. Only particle is oscillating. Similarly, particle is oscillating in its own position, but it is not transferring from one place to another place. But in liquid state, particles leave their own position and can go from one corner to another corner. Suppose this is liquid water. Particle of this place can move here, then upward, then go down, then it can come back to here. It can move from one corner to another corner. But it takes long time to reach from one place to another distant place. But the particle of liquid are executing translatory motion. In solid state, they do not execute translatory motion. What is the meaning of translatory motion? To leave their own place is translatory motion. Particles are not changing their own position. But in liquid state, particles are continuously changing their own position. So such type of motions is called translatory motion with some finite velocity, not with some finite speed. And also from place to place, the speed of particles does not remain same. So maybe it is 1 centimeter per second, this motion is by 1.5 centimeter per second, maybe by this it is 0.1 meter per second. Speed and direction is always changing. This type of motion of particles is called random motion or zigzag motion, rapid random motion or zigzag motion. And in the gaseous state, this speed is quite high and they are executing rapid random motion. So there is one difference between solid, liquid and gas. Difference of speeds, and another difference is of temperature. Temperature of vapor, you can at 1 atmosphere up to any high temperature. Temperature of steam can be raised up to many thousand degrees Celsius. Many thousand degrees Celsius temperature you can have. There is no finite limit of higher temperature. It will depend upon pressure and many other things also. Generally, when water boils in your home, in open kettle, its temperature is about 100 degrees Celsius. In Chandauli, it will boil at 99 degrees Celsius by other reasons, but we assume the boiling point of temperature 100 degrees Celsius at 1 atmospheric pressure. At 1 atmospheric pressure, what is boiling point of water? 100 degrees Celsius. And the steam generated over surface of water will be of 100 degrees Celsius. But you can heat steam up to 3, 4, 6, 7,000 degrees Celsius. Now the question arises, why we do need to heat steam more than 100 degrees Celsius? In turbines, after boiler, in boilers of powerhouses, in boilers of powerhouses, water boils. Boiling point of water in boiler is 550 degrees Celsius. In your pressure cooker, the boiling point of water is 130 degrees Celsius. But in boilers, the boiling point of same water is 550 degrees Celsius. Why it is so? Because the pressure here is for more than 110 atmosphere or 200 atmosphere, 110 atmosphere. There is quite high pressure, and then this generated steam has its temperature 550 degrees Celsius. But this steam is not capable of running turbines in good efficiency, because heat content in this steam is not as much as we need to drive a steam turbine. Then what we do? This steam is again heated in the furnace, and its temperature becomes around about 2000 degrees Celsius. It also depends upon the quality of coal you are using in your thermal power station. As is good quality of your coal, you can heat this steam up to more and more temperature. More and more temperature of this superheated steam. This steam is called superheated steam. As is greater and greater temperature of your superheated steam, you will get more power for the same turbine. For the same unit of turbine, for the same structure, you will get more power if your steam is highly superheated. And this turbines, this steam runs the steam turbine. Suppose your steam turbine is of 500 megawatt. It will run, and after running turbine, the steam gets cooled, and by some process, some water is also exhausted, and remaining steam we again pump it to the same unit to save our thermal energy. But it's quite complicated. As you grow in higher and higher classes, you will see the thermodynamical effect and steam properties in higher classes. Here, only you can see we cannot limit the temperature of steam. It may be many thousand degrees Celsius. But the furnace available practically is not more than 2500 degrees Celsius in our country. We can heat steam up to 1500, 1600, 2000 degrees Celsius, not more. Because we do not have such ovens, because we do not have such furnaces of very high temperature. So we cannot heat it. But if furnaces are available, we can heat the same steam up to very high temperature.